Hello everyone. So this is our machine learning final project presentation, and the topic that we chose for this project was fraud detection or financial fraudulent data detection. And my team consists of two members, me, myself, Jaron Philip, as well as Karthik Ashok Vora. So financial fraud is considered as a deceptive tactics that people use in order to gain financial benefits by scamming other people. And this has become a widespread menace in companies and organizations worldwide. It has become an important risk to facing financial institutions as credit unions and banks in particular. Now, combating fraud with traditional techniques like PINs, passwords, and identification systems, however, has become inadequate in modern banking systems. Now, with the advent of AI and machine learning techniques, this machine learning approaches have helped to intelligently detect fraudulent transactions by analyzing a large amount of financial data. Fraud detection is a classification problem, as the data that we have in hand can either be fraudulent or it is not. Now, going to related works, like there have been many other related works. Like this is something that has been happening for the past decade or so. So there's been many people who have delved into this particular field. One such person is Lamar, who has done an analysis of several forms of credit card fraud, such as bankruptcy and counterfeit fraud. Then there is Zhang and So, who looked at machine learning techniques for fraudulent transactions, including stock market and other financial industry fraud detection procedures. An in-depth overview of detecting credit frauds was done by Papat and Chowdhury. There's more information that is available in the paper that we have created, so feel free to go through that for the same. Moving on, the dataset that we chose for this project was from Kaggle, and it was in JSON format. The file type was text. It had approximately 786,000 rows and 29 columns. These were the features of the columns that are available as part of the Kaggle dataset, and these are the columns, and the most important among them is its fraud, which tells us if the data is fraudulent or not. Moving on, so as with any other data science or machine learning project, the data that we obtained had to be properly cleaned in order to make sure that the data doesn't have any hiccups. So in this case, the columns which consists of null or blank values were properly removed or eliminated from the dataset. Also, we got rid of some of the features that were not required. For instance, account number, customer ID, merchant name, card last four digits, etc., were removed as they did not play much of a role in training our model. Now, we also imputed missing data with the most frequent values that occurred in a particular column. Also, some columns were combined into a single column. For instance, entered CVV and card CVV were two separate columns. They were combined into a single one. So it's told us if the CVV that was entered by the user was same as that of the card CVV or not. It gave us a true or false values of zeros and ones. Moving on to the exploratory data analysis. So this is basically a heat map which gives us the correlation between the various variables that are or features that are there in the dataset. As you can see here, available money as well as credit limit has got very high positive correlation. So we basically did a scatter plot on them in order to show their correlation. We also created some other graphs showing the relationship between different features that are there in the dataset. So an extensive explanation has been provided for this in our paper. I'm not going through it, each of these graphs again. So moving on, the next slide is about feature engineering. Feature engineering basically refers to taking raw data and converting and making use of a feature extractor to extract the corresponding features that are needed by an algorithm that are needed by the machine learning algorithms. So yeah, the extracted columns or features include year, month, day, minutes, hours, seconds, etc. Now, some of these features were textual in format, but however, we needed a numerical format of data so that they could be directly fed into the models that we were creating. So there are two techniques that we could find that did the same for us. One was label encoding, and the other one was one-hot encoding. So we basically made use of one-hot encoding. One-hot encoding basically refers to converting categorical data variables to numerical columns. It improves predictions as well as classification accuracy of a model. Label encoding is something that we have reserved for the future. For instance, if we are going to be working more on this particular project, probably we will replace one-hot encoding with label encoding. Now, this is an example of one-hot encoding. Moving on, Let's take a look at standardization of data. So even before we move on to model training, the data has to be properly standardized. And this is done by making use of z-scoring. Z-score stands for z is equal to x minus mu by sigma, where x is the observed value, mu is the mean of the sample, sigma is the standard deviation of the sample, and z stands for the standardized score. So for each data point, the z-score tells us how far the data point is from the mean or the median. So that's it from my part, and proceeding from the next slide, Karthik is going to be explaining about some stuff.
Hi, my name is Karthik and I'll be taking over the presentation from now. So the next step that we have is model training, which is our ultimate goal in this project. Like all the steps we did so far was about preparing data for model training. So the first thing that we have to look at is, let's say, our data. And we have a look at the data and we can see that it's clearly an imbalanced data, like that only we have 1.6% of fraud data in our whole data set. So we actually decided to go with two approaches to counter this. First one is called upsampling. So upsampling is basically taking the minority class data set and like upscaling it to match the majority class data set. So for example, we had like one data, which is the fraud data, only about 9,319 rows. So when we upsample it, it is now equal to 5,80,453. This is just done by duplicating the existing data of with label 1. The other approach that we can try is downsampling, where we take the non-fraud data and we reduce the number of rows from 5,80,453 to uh, 9,319, as we can see in this diagram in the downsampling part. So we actually decided to go with both the approaches and we have results from both the samples. Okay. So the algorithms that we used are following, which is naive Bayes, logistic regression, decision tree, and random forest. Okay. So in case of imbalanced dataset, the accuracy of a model is not the best thing to consider because it could be like, the model could predict everything at zero and we'll probably get something like an accuracy of 90%, which is incorrect because which is not our goal. Our goal is to predict fraud data. Okay, so that's why along with accuracy, we will consider some other metrics as well, like precision, recall, confusion metrics, and AUROC. So precision is basically what proportion of your positive identification was actually correct. Recall is basically the fraction of samples from a class which are correctly predicted by the model. And confusion metrics is basically the table which tells you about your true positive, true negative, false negative data. Next one, there's this, which is AUROC. Now, this represents the how likely your model is going to distinguish between your fraud and non-fraud data set. Okay. So the ideal, basically, AUROC curve that we are looking for is something like this. So it is like perfectly able to distinguish between a positive class and a negative class. Okay. So let's look at the results now. So here's the result for naive Bayes. Now with the upsample data, we only got an accuracy of 33%. With downsampled, about 55%, which is much, much better. But let's see the main thing that we are trying to predict, which is the predicting the fraud data. Now in predicting fraud data, the upsampled data has a recall of 81%, which is good, but the precision is pretty bad. It's 0.02. Similarly, for downsample data, the recall is 0.99 for predicting one, and precision is like 0.52, which is fairly better than the upsample data set. Okay. But still, I think 55% is pretty low accuracy for any model. So we will go to some other model, try some other models. And as we look at the ROC curve as well, it's not even close to the ideal curve that we intend to have. Okay. Our next thing we tried was the logistic regression model. And, if you look at the upsampled accuracy, it's 90%. Wow, it looks amazing. But this is probably like not the right factor to consider because when you look at the recall value of it, it's just 0.27% and the precision of 0.05% while predicting fraud data. And our ultimate goal is predicting whether the data is fraud. Yeah, so this definitely falters. And same, if we look at the downsample data set, we are actually getting a better results over here with a precision of 66% and a recall of 70%. I think the downsampled version did pretty well here. And if you look at the ROC curve, again, both the curves are a little far from the ideal curve that we intend to have. Now let's look at the decision tree algorithm. The decision tree algorithm, again, I think it has similar issues to what we saw with logistic regression, high accuracy, low on recall precision. For the downsample data, maybe slightly better, okay, precision of 60%, recall of 60% nearly, and I think it did pretty well. I mean, we have observed that the three base algorithms are doing better at predicting imbalanced data set labels. Yeah. So the next thing we tried was an ensemble algorithm. An ensemble algorithm that we tried was random forest. Now, random forest upsampled, same issues. I mean, it's pretty bad with the recall and precision. Now, let's look at the downsampled one. Oh, everything is like 70% plus accuracy, precision, recall. And this seems to be like doing pretty well. And if we look at the AUROC curve, slightly better than what we have seen so far. So we definitely like decided to explore random forest a little bit more. Like we also tried the same, like we tried to explore other models as well with hyperparameter tuning and k-fold uh, k-fold cross validations. But even then, we were not getting the exact result that we intended to get. But with random forest, when we tried to do those, we'll see the result soon. So let's have an analysis of what we have done so far. Like we can clearly see that downsampling seems to be producing better results. Tree-based algorithms seem to be performing better, and random forest like gave us the best result. And so that's why, as I said, we will do the hyperparameter tuning and k-fold cross validation on the random forest algorithm. And as we can see, I have used grid search CV, which is an sklearn library, to do the hyperparameter tuning. So basically, what we do to this library is specify a grid of parameters, and we ask it to search for which parameters will give us the best result for random forest algorithm. And these are the parameters that were suggested by the grid search algorithm. It took about couple of maybe 3 or 4 hours actually to completely to provide us with this set of data. That these are the best parameters for the random forest algorithm. So let's use that in our algorithm and see the results. As you can see here, the accuracy, precision, recall, they are slightly better, like from 72% to 73% now. Definitely a lot better. But if you look at the ROC curve, oh my God, it's really the ideal curve that we intended to have. So yeah, this exactly is what we were looking for. And so random forest algorithm is definitely the best one that we have tried so far. For future extensions, we'll like feel like we should try more algorithms like SVM and other tree-based algorithms. And similarly, like there were too many dimensions that were involved while we were using it. So we could implement something like principal component analysis or variance inflation factor, which we kind of already tried to do, but we were running into some issues with the time taken by it to like give us the results, so we could not explore it further. And we could also try something like label encoding instead of one hot encoding. I think tree-based algorithms should be able to handle that well as well. And the other thing is with the grid search CV, as I said, we tried a few parameters and it took about 4 hours for us to get a result. So we could try with more parameters, run for a little longer, and see if we can get even better results with the grid search algorithm. So and in terms of like individual responsibilities, like mostly for the data preparation part, we kind of worked simultaneously. We connected with each other and worked on all parts of it. Then post that, we had four algorithms. We like divided the work. Like one of us worked on two algorithms, the other worked on other two algorithms, and basically then we had the paper and the report part. Jerin primarily worked on the paper report. I worked primarily on the presentation part, but each of us like reviewed each other's work and then we edited each other's work. So that's about it for me for this presentation. Thank you.